Morning. I am Nicole Testa-Boston, the Deputy Director of the FIATech Consortium. And on behalf of all of us at FIATech, I want to thank you for joining us today. We have an exciting hour set aside to talk about life cycle assessment methods for complex systems. This work and Professor Lepek were awarded the SETI Award at our recent gala in April in Arizona, and he's going to be sharing a little more information and details on that work. Before we get started, though, I do want to let those of you who may be joining us for the first time know a little bit about this system and how we work here. You will have noticed you have a dashboard on your screen that is unique to you, so if at any time you want to minimize it, you can click the orange arrow button at the top of the Grab tab, and that will minimize it and get it off your screen. To access it, again, you simply click on the arrow, and it will maximize. There is also a questions tab on this dashboard. We do ask that if you have any questions or would like clarification on something that's being discussed, to just type that in throughout the presentation, and then again as time permits at the end of the hour. I will be forwarding those questions to the presenter. I will not say who is asking the question or what company or organization that person comes from, so please feel free to use that tool throughout the entire presentation. And last but not least, we will be recording this presentation, both the slides and the audio, and we will post it on the FIATech website at fiatech.org later this week. Give us a few days to package it up and post it, but we will have it online. So with that, I want to go ahead and introduce Professor Lepek. His research focuses on the integration of sustainability indicators into engineering design, ranging from materials design, structural design, system design, to operations management. Such sustainability indicators include a comprehensive set of environmental, economic, and social costs. Recently, his research has focused on the design of sustainable high-performance fiber-reinforced cementitious composites and fiber-reinforced polymers, the impacts of sustainable materials on building and infrastructure design and operation, and the development of new life cycle asset applications for building systems, transportation systems, water systems, and consumer products. Michael joined the Stanford University Department of Civil and Environmental Engineering faculty from the University of Michigan Center for Sustainable Systems, where he was a research fellow at the School of Natural Resources and Environment. He received his doctorate in materials engineering from the Department of Civil and Environmental Engineering at the University of Michigan, Ann Arbor. He also received his MSc in structural engineering from the Department of Civil and Environmental Engineering at the University of Michigan, Ann Arbor, and his MBA in strategy from the Stephen M. Ross School of Business at the University of Michigan. His industry experience lies in the design and construction of interstate highways and bridges, along with the design and construction of residential high-rises and seismic zones. So thank you very much for joining us today, and let's get started.
All right, thanks, Nicole. I really didn't know you were going to read that whole thing. That was a bit longer than I had planned on. So what I wanted to discuss today was a little bit about what.
Can I interrupt you? I'm sorry.
Yeah, sure.
You're kind of breaking up. Are you?
Yeah, I'm not sure why that is. I'm on a landline because I was hearing you breaking up as well. But is it getting better now? I've adjusted the cord. Can you hear me okay now?
No. It's a little shaky.
Little shaky.
Oh, there we go. There we go.
Okay. Let me try this. Is that getting? Hello, Nicole?
Yes.
Okay. Can we try this?
We did just check this all, everybody, and everything was working fine until we went live.
All right.
Yeah,
is that any better, Nicole, or not?
It's a little bit better. It's kind of shaky, but it's better.
Okay. If it gets too bad, we'll try it again. All right.
Okay.
Okay. Yeah. Until we went live, we had a really nice conversation. So I wanted to talk a little bit about what we do in the classroom here at Stanford, and then also how that integrates with the corporate partners that we have in with this class. So what we're trying to do here is integrate life cycle assessment and quantitative sustainability methods into complex systems analysis. And those are any systems that involve lots of parties and have very nonlinear responses. In particular, we'll talk about applications for innovative construction. But the place that I start the class every single year is by asking the students, what is sustainability? And invariably, I get from 50 students, I get 60 different answers that range from, well, that's LEED, to somebody who recites to me the Brundtland Commission's definition of sustainability that says that we have to be doing things that do not compromise the ability of future generations to meet their own needs, which is very nice, but really tough for us to operationalize and to make decisions on a day-to-day basis. For lots of folks, sustainability comes down to the products that they think embody sustainability or the brands that they think are closely associated with sustainability. So that could be anything from electric cars or hybrids to biodegradable products to Energy Star and cradle-to-cradle certification. And of course, in the building sector, a lot of that focuses on LEED and the green building councils around the world. But in many regards, these are just proxies for sustainability, and in some cases they're good proxies, and in some cases they're not very good proxies, and that's something that we try to focus on a great deal when we're discussing sustainability. The way we accomplish that here is by looking at the entire production, consumption process, and all of the material and energy flows that are associated with that. And so we start by looking at raw material acquisition, if we're going to be constructing or producing any products, starting back from where we get all of our resources out of the ground, where they're processed, how they're manufactured, assembled, or constructed, how they're used, what the service looks like, how they're retired and recovered, whether they're recycled, remanufactured, or finally disposed. And so then what we want to do is put together a set of metrics that describe the ability of our ability to continue to do those processes in perpetuity without harming ourselves or the natural ecosystems around us. So I always, when we talk about sustainability, I want to talk about the specific metrics that we're going to use to describe that. And oddly enough, we say that sustainability begins with us. The reason for us to do any kind of sustainability work is to make human life better and to allow our species to exist in perpetuity. It's a very anthropocentric viewpoint, but in many regards, it's due to our guilt that we're doing this sustainability work. And so we have a population here on the planet, and we have a set of needs that we're trying to meet to clothe ourselves, shelter ourselves, feed ourselves. And in order to do that, we've come up with a set of highly complex production and consumption activities that are there to provide all of our needs. And to do those production and consumption activities, we have come up with a very complex set of material and energy flows to get goods and services where they need to be all over the planet. And of course, when we engage in those activities, we force changes on our ecosystem, whether that's due to resource depletion, whether that's due to ecotoxicity, whether that's due to something as controversial as global climate change. Everything we're doing does have an impact, if not regionally then globally, on the world around us. And so what we're really trying to do with sustainability is to measure our ability to meet those human needs that as a population we've forced on ourselves. And so we come up with a set of indicators that gauge every single piece of that system. When we talk about our ability to meet human needs, those are social indicators. When we talk about our production and consumption activities and the ability for us to keep doing those are economic indicators. When we talk about the material flows and the changes in the ecosystem that are caused by those activities, we call those ecological indicators. And so for those of you who have heard of the sustainability triple bottom line, this is where that comes from, where you've got economics, environment, and social impacts. And so these are the types of indicators that we use when we're talking about sustainability. But where does that relate to all of these labels and things? Well, we'll talk about how those actually connect. And then there's one type of green here in the United States that we're all very focused on. That it has to be part of the equation for us to make sure this makes sense, because otherwise it's a very altruistic thing, and that's really not the point at all. So in the outline today, I wanted to talk about what quantitative sustainability assessment is, in particular life cycle assessment. We'll talk about how to link that to industry through the class that we have here, CE 226, and then finally a summary. So there are a number of standards that govern life cycle assessment, at least process-based life cycle assessment, and those come from ISO, specifically the 14040 series standards for life cycle assessment, and there's also 14020 that looks at environmental labeling. So within that standard, we're guided to look at all of the different pieces of the supply chain going back to that raw material acquisition. And so we'll look at every single piece of that, and also those T's represent the transportation between each one of the nodes of the supply chain. We'll draw a boundary around all or part of that system, and then we'll start to measure things. Everything that comes in and everything that goes out across that boundary. Primary materials, recycled materials, primary energy. We may also measure labor and capital. And then coming out, we measure things like air pollutants, water pollutants, solid waste, the products that we're actually making, because we're doing all this for a reason, and any co-products that are also produced. Those are things that have economic value, but don't actually weren't actually what we intended to make. So I refer to this as the 6-phase framework. I said it starts with raw material acquisition, then material processing, manufacture, use and service, and end of life, and then transportation throughout. And so within this framework, we want to account for all the inputs and outputs in each of these life cycle phases. So what does this type of analysis look like? And this is exactly what we go through and we learn to do in the class that I teach here, and in the projects that students do with corporations. This was an example that we did for the Monterey Bay Aquarium Research Institute. For those of you who are out here in Northern California, or for those of you who have visited, you may have been to the Monterey Bay Aquarium. They have a tremendous exhibit there for the sea life here in Northern California. They have a research institute that they use to study the fish and keep them healthy. And also, when they're cleaning the tanks and things, they have some large aquariums that they keep all of their sea life in when they're doing maintenance. And so they wanted to build some new tanks at their facility, and being an ecologically sensitive and environmentally active partner, they wanted to compare the construction of a regular concrete tank, shown there on the left, versus a tank made of a fiber reinforced polymer. And they wanted to know, they had 2 bids for these, and they wanted to know which one would be better for the environment, given that the price differential was so close. So it starts with the construction. The students and the researchers have to start with constructing a process flow diagram that describes how each one of these systems is built and used and maintained and finally disposed of at the end of life throughout its entire life cycle. And so here along this process flow, we can see it divides up into the material production parts, construction and fabrication, a use phase, and an end of life. And then if I blow some of these parts up, we can see that the concrete tank requires raw materials of limestone, cement, gypsum, pig iron, timber for formwork. And then we use that to make concrete and rebar and formwork. And then for the FRP, requires inputs of electricity and sand and borax and fuel to make glass, and then electricity, oil, and fuels to make our FRP resins. And so we'll go back all the way through the supply chain to the extraction of those materials out of the ground. So then we'll put together a high-fidelity supply chain model. In this case, this is the supply chain for the high fly ash concrete that they were planning on using. And we account for all of the inputs going in and going out to get that, in this case, that concrete from its from limestone quarry all the way to putting it onto the site. Now, of course, we don't have a very good, most people don't have a very good idea of what it takes to extract limestone and how much energy and material and what emissions are associated with the removal of limestone or the production of electricity or the production of fuel oil. And so what we rely on are a number of industry data sets that give us this information on aggregate for the entire industry. And so those are called life cycle inventories. Here we're looking at the electricity life cycle inventory for the United States. And I'm going to blow up a small piece of this that shows that for the production of 1 megajoule of electricity, that's our functional unit in this case, we can see what the average emission is from a U.S. power plant. So we can see here everybody's favorite emission, carbon dioxide down there, fossil-based. You can see that to make 1 megajoule of electricity, we release approximately 183 grams of CO2 on average. And so we can use data sets like this to go back and say, okay, how much electricity was consumed in the production along the entire supply chain, and then we can compute on average how much emission and what emissions are associated with this activity. Similar data sets for all kinds of different materials, not just energy. So here we're looking at a process flow diagram for the production of polymers. You can see that we bring most of our polymers. They come from crude oil, natural gas, and brine. And through all kinds of chemical processes, we can make whatever we want. In this case, we're looking at the life cycle inventory, or LCI, for a high-density polyethylene resin. So here you can see that in order to make HDPE resin, 1 kilogram of it, it requires approximately a total energy input of 77 megajoules. And so if you know how many kilograms of material in your quantity takeoff, you can start to determine what the impact of your project is going to be. Once again, here we're looking at the air emissions associated with that same kilogram of high-density polyethylene. If we look once again at CO2 there, roughly a kilogram and a half of CO2 is released from extracting the oil from the oil well to producing 1 kilogram of high-density polyethylene. So every time you look at one kilogram's worth of HDPE, there's about a kilogram and a half of CO2 in the atmosphere associated with that production. So once we have our process flow diagram and our quantity takeoff from our structures, then we can start to get a larger idea of what the overall impacts are going to be for these processes. So then we'll take all of those specific emissions, all of which are listed there in a big, long laundry list of impacts, and we'll start to group those together into input-related impacts and output-related impacts. So input-related impacts are going to be things like abiotic resource extraction or biotic, so renewable versus non-renewable resources, and also land use. For output-related categories, we're going to take all of the emissions that relate to global change, global climate change, and we're going to group those together. Those that are related to ozone depletion, those are related to human toxicity, and we can group these together into a relatively small number of impact categories so that we can start to make choices between them. And so we'll come up with graphs like this, that in this case we're looking at the impacts for a couple of different consumer products, where you can see on this spider chart we've got 3 different products compared, the red product, the blue product, and the gray product. And each of these points on this spider chart show a specific impact category. So at the top, ERC is energy resources consumed, and as I move clockwise, you'll see global warming potential, acidification potential, so that causes acid rain. Criteria pollutants cause asthma in the population. Solid waste is just what's going to landfill. And total material consumed is the total amount of abiotic and biotic inputs. And so you can start to make comparisons between products or product decisions as to what you want the footprint to look like. And of course, in most cases, you're going to be going with a smaller footprint. Now, this isn't quite the end of the line in how we do this, because this graph here, by default, assumes that each of these impact categories has an equal weighting, in that global warming potential emissions are just as important as acid rain emissions, are just as important as solid waste creation. And we know that's not the case. And so we'll often weight these through various weighting schemes to get an overall indicator of what is the best possible choice. So then we'll take those results, and of course we can quantify them as well to see what the percentage differences are. And so here we're looking at all those same impact categories: acid rain, carcinogens they release, energy resources consumed, biological oxygen demand in water systems as eutrophication, greenhouse gas emissions, ozone layer depletion, solid waste, smog creation. And we can quantify the impacts associated with each of those in their various units. And then we look at the percentage differences, and we can start to see if indeed one system is better than the other from all the way back at the initial start of the life cycle. So then at that point, we want to get pushed forward to drawing some conclusions and making some recommendations. And so, like I said, we can start to weight among the various factors, identify major burdens and impacts, and then select among the alternative design decisions. So at that point, I don't know, Nicole, were there any questions that came up, or are we doing okay?
Right now, we are okay. We have no questions, but folks who do have any or want some clarifications, please use the questions tab and type those in.
Do you have any questions, Nicole?
No, we're all set.
Okay, good. All righty. So that's kind of the overall structure of the class, and what we try to accomplish over the course of the quarter. So after that, the major focus of the class is a linking to industry, and that's done through project-based learning, where we bring in corporate partners to work with small groups of students, and the corporate partners have identified a specific project that they're working on that they think that an environmental analysis like this would really benefit. And so therefore, what we're trying to accomplish is a training of an entire new set of engineers, construction managers, structural engineers, product engineers, MBAs, that are cognizant of the methods that we can use to analyze for environmental sustainability, and then quantitatively manage towards that quantifiable environmental goals. So in this case, I wanted to talk about one of the projects that one of the student groups did. This was a project that was proposed by PPG. Or PPG makes glass fibers and other glass materials, and they were proposing a new type of bridge deck that they wanted to try to bring out to industry, and they were proposing this as being a very green and environmentally beneficial product in comparison to the way that bridges are currently constructed by the DOT. So the motivation was that they wanted motivation for this project was they wanted a life cycle assessment and also a life cycle cost comparison to support some new product development. And so they have a regular concrete deck with a variety of attributes, having the cement and the sand and the steel reinforcement, relatively slow curing, permeable to water, had volume changes, and the corrosion was affected by the pH and the chlorides. And PPG was proposing a new deck that was made of a different type of concrete, a grancrete, with a composite reinforcement, a fiberglass mesh that was a fast curing deck, impermeable to water, high tolerance to temperature change, and relatively no impact from pH changes due to salting of the roads, and which will often lead to corrosion. And so the students needed a way to try to gauge what the impact of these two systems was going to be, and then try to make a decision throughout the entire life cycle of which one was indeed better. So to do this, they said, well, we need a way to be able to determine what the impacts of the pre-construction and construction phases are going to be, and then we need some way to manage those over the course of the project, determine what they're going to actually be on the project site, and then maybe enact some controls to make sure that in fact those two things line up very well. And so the way that the student group in this case proposed doing that was combining a 4D BIM model with a life cycle assessment model, as we learned in class, to come up with a set of time-dependent impact budgets over the course of construction so they could see and model how impacts were going to accrue as a facility, in this case the bridge deck, was constructed. And then they can combine that with some job site data they had gotten from Caltrans and their same life cycle assessment model to figure out, is that really the way that emissions occur on a job site? And then they proposed a number of methods to engage in impact variance control on the job site. So like I said, they started with combinations of a 4D BIM model and an LCA to come up with a time-dependent environmental impact budget. This is what the predicted impact of the construction was going to be as it was completed. This was done at the activities level of the work breakdown structure so that they had a chance to really kind of tie the life cycle assessment data sets that were out there to accounting level based activities at each part of the job site. So then they came up with a structure to integrate the BIM model and the life cycle assessment. So they created a BIM model for each of these two bridges, a 4D BIM model, that interacts with a user interface for their life cycle assessment program as it shoots out in this case, a CSI master format code for what that activity is that's being done. In this case, they were installing some riprap. That user interface interacts with a code array that lists all of the materials associated with that activity, and it also denotes the crew that's going to be needed for each of those activities. Then that interacts with a life cycle inventory data set that ties the life cycle impacts associated with each of those activities or materials inside the activity code and returns the impact of that specific activity. And so you can see in this case, looking along the top line there, that in order to install riprap, 1 ton of it, the impact was about 1.7 kilograms of 1.7 tons of CO2. So then, just as an example on this project, they came up with their construction activity list, which had a partial quantity takeoff of all of the work that was going to be done in order to do one of these Grandcrete installations. And so then they come up with an activity-based environmental impact assessment so that they know for every single construction activity that was being done what the global warming potential, the energy consumed, the acidification, biological oxygen demand, or eutrophication would be, so that they can then link that up with their activity timeline to come up with a time-dependent impact accrual budget for every single one of the environmental indicators associated with the project as they're accrued throughout the construction work. So this gives them their basic approach to controlling impacts. So then they needed to come up with a system for actually tracking these. So that in that case, as I mentioned, they were combining a life cycle assessment model with with some job site data to come up with a job site emission tracking approach. So there they were getting information from from Caltrans and also the Michigan DOT. But they had also proposed the use of some time cards, GPS tracking equipment, time-lapse photography, a variety of ways to quantify exactly what equipment is being used on site and how long it's being used, what idle times were, what work is being done at each given time, and of course they can from that you get your ongoing accumulated work impact. And so these are the kind of data sets they were getting off of the job sites that show the specific type of equipment being used, its run time, its idle time, and of course by linking that with our life cycle assessment model, we can get a up-to-date real-time accrual of environmental impacts on the construction site so that we can start to compare those to our budgeted numbers and actually work to manage those to the lowest possible impact that we can using relatively traditional construction management techniques. And that's where they propose the environmental impact variance control over the course of the project. So this is what that ends up looking like as far as the impact lines that were created. And then it just uses traditional schedule and variance control to manage impacts over the course of the project as you start to reach completion. And by modeling how that would be done, they could come up with some pretty good estimates for what the predicted impacts for these specific projects were and what the actual accrued impacts would be based on how work had been done traditionally here in California, and to see if, in fact, these two, how these two bridge systems compared. So the application for the PPG product was then optimized using an LCA model, this LCA model that they developed through the class. And so you can see just their schematic of their bridge that they were working at. But so the initial impacts that were associated with the application showed a very poor performance for the PPG system. You can see that in terms of impacts there, the blue line and its associated lines are significantly higher for climate change and fossil fuels, so on respiratory inorganics. But then after implementing the system and optimizing the PPG system for the time of construction, for the impacts that were being accrued, for the supply chain that was being used, they significantly reduced the impacts without changing the cost of the system. And I specifically picked this example because it has such a dramatic reduction in impacts. This also accounts for some changes in traffic and some recommendations on what type of structures you want to apply these PPG bridge decks to. And so here what we're looking at is the prediction of life cycle cost for each one of these two systems. And this cost includes environmental impact costs and social impact costs for each of these two systems. And so their recommendations were that at a relatively small number of vehicles per day, it makes sense to install a concrete deck because the overall single costs are lower. That's simply because the vast majority of environmental impacts and the costs associated with them accrue from the traffic that is held up in delays on the construction project. The actual materials being used are relatively small in terms of the scope of the scale of their impacts in comparison to the traffic. So after a certain number of vehicles per day cross the bridge deck, it makes far more sense to implement the PPG system. And so along with the optimization that was done, we came up with a set of, the students came up with a set of recommendations for how you would actually approach a DOT to say these types of projects are good, and those other types of projects that have low traffic counts are poor. And so that way we could make some very strategic recommendations for what materials to use, what supply chains to use, what construction practices to use, and also what projects to actually bid and go after that made sense from the standpoint of an environmental sustainability argument. So I don't know, Nicole, at this point, are there any big questions, or are we still good?
We do have some questions.
All right.
Yes. Question number 1, similar to BIM comparison, are there plans to link LCA and ISO 15926, which is the standards for the industrial power process plants?
Yeah. So as far as I know, there aren't any plans to do that, but if folks are interested in doing that, I would love to talk about that more. But that's not something, as far as I know, that's actively being sought out. But I think it could be a really exciting thing to do because, to me, it makes some sense to be able to do that. So it doesn't really answer the question to say how you might be able to do that, but as far as I know, there aren't any big plans to do that at this point. But I think that'd be a great deal of fun.
Okay. This question came in about 15 minutes ago, so it refers to the earlier part of your presentation, but they want to know how your materials share the same mechanical characteristics.
Oh, okay. So In that case, it goes back to a question of functional unit, and that was something I didn't go into a great detail on earlier in the presentation. So when we're doing these comparisons, it's absolutely critical that we're comparing apples to apples. And so therefore, when we're doing two comparisons like this, we specifically set what's called a functional unit very carefully. And this is the quantitative basis by which we're going to make the comparison. So in this case, the functional unit was a bridge deck that had to carry a minimum vehicle load of, I believe it was 50,000 vehicles a day for 75 years and meet all of the AASHTO bridge design requirements as far as being able to meet reliability requirements and be designed according to the AASHTO bridge code. Now, when we start to model these two materials, because the PPG deck lasts quite a bit longer, we have to model a maintenance scheme and a repair cycle. And so the concrete deck has a much more rapid repair cycle. So every 15 to 20 years, there has to be patching or a small overlay or shallow overlay or a deep overlay to keep the bridge deck meeting its functional requirements. And so all of the impacts associated with that repair scheme will be taken into account. The PPG deck, in order to get to that 75 years, only required, according to the durability models that we have, only required one repair. And so that's where you get the benefit of the difference in the materials. The other benefit is that in order to meet the structural requirements associated with the AASHTO design loads, we can make the PPG deck thinner, and so then that's where you'll get the material comparisons. And so because this is a full life cycle analysis, we do end up leveraging any differences in materials, but that's the way that they're demonstrated in that throughout the entire analysis. So I hope that answers the question.
Thank you. A couple more. Isn't it just as important to measure the impact of removing the structure again and restoring the site to its original state as it is to measure the impact of construction and use of the structure? I didn't hear any mention of this aspect. Thanks.
The impact to return the structure to its original state. So I'm thinking what they're asking there is wanting to get the structure all the way back to the natural state and then building the system new from there. This isn't something normally we would include in an analysis like this, because if we go back to the definition of what sustainability is and kind of looking at the populations and meeting human needs and making these and using these indicators, the goal is not to return systems to their natural state. Their goal is to continue to meet human needs while not damaging natural ecosystems that we live in beyond or to a point where they can no longer function. Now, as I had mentioned at the start, this is a very human-centric view of sustainability, but is currently the way that all sustainability metrics are viewed, in that we're doing this to enable human populations to survive in harmony with the natural ecosystems, while we're still meeting our economic goals, our social goals for equity, and the environmental goals for us to survive. So we would never actually want to know what the impacts are to return a system to its natural state unless we no longer needed that economic asset, and that wasn't the case here. All we're doing is making a comparison to keep the system going in its ongoing state while minimizing environmental impact. So I hope that answers the question. If it doesn't, please.
He added more to it and just said yes, and these needs do change over time.
Oh, most certainly, and so we would want to. There's a great deal of uncertainty that goes into these analyses, and that's something we haven't really gotten a chance to discuss yet. But we will want to take that into account for sure.
Okay, and last question before we move on. Do you think your LCC methodology can be replicated in different industries? My impression is that your setup is capital hungry or capital intensive.
Yeah. So as far as the setup to do the analysis, no, it can certainly be stretched to other industries, and that's actually a really good transition into all of the corporate partners that we had this past year for the class. And so we did projects with all of these corporate partners. And so you can see a range of industries, whether it's DPR and WebCore, PPG, of course, all the way to Cisco and Hewlett-Packard. And so while this project was very focused on construction, certainly the framework and the lessons that are taught through the curriculum and how we do this, and also the software that we use as the engines underneath this with the life cycle inventories are very applicable to lots of other industries. And it just takes some work and some knowledge to be able to tie those existing data sets and inventories into the current or to the industry that you want to apply it to. One example that we've done a lot of work with is Steelcase, furniture manufacturer, and in that case we had tied these types of decision-making tools into their product design cycle, and so we created a group of students created some Excel-based tools for the designers at Steelcase to be able to quickly evaluate the impacts of different material choices in their furniture designs. Now, within the bridge deck example, that modeling was very focused on the use phase of the bridge, how much fuel is consumed by the cars going over it, and modeling traffic delays and things like this. Whereas for something like furniture, there's not a great deal of use phase impact. Once it's produced in the factory and shipped to you, that furniture doesn't have a great deal of impact aside from maybe recovering it over time. And so we had to do a little bit of modeling as far as the longevity of fabrics and things. So in that case, it was completely transferable with just the kind of shifting of this tool or these data sets into a different format to interact with those designers. So I hope that answers the question.
Sorry, I had you on mute. Yes, it did. Thank you.
Okay, sounds good. Anything else at this point?
No, we're good right now. Thank you.
All righty. I actually don't have that much more to go, so we're going to have plenty of time for questions. So those were all the corporate partners that we had this past year, and of course the previous few years we've done this. It was this many, and so you can see how. And we also get a lot of folks coming back that are interested in working with the students in the class. Why do the corporate partners come and help with this? Well, you know, in talking to them, we've seen. So this was a corporate value proposition list associated with environmental initiatives that was put out in 1999 by the Global Environmental Management Initiative. And in working with all of our corporate partners, we've seen that this has been experienced by a large number of these, a large number of our partners. Not every one of our partners is going to get value in every single one of these, but often they will see value in helping with regulatory compliance. To say that when they're working with the EPA or their state Department of Environmental Quality, you know, the fact that they're showing that they're engaging in analysis like this and trying to reduce impacts on a life cycle scale gives them a bit more leeway with regulatory compliance. In the case of PPG, it certainly increased their operational efficiency of the production systems to understand where their energy was going and where their emissions were coming from, and they definitely tweaked their supply chain. As far as environmental toxin releases go, it helps in risk management and understanding where the potential carcinogenic or toxic emissions are associated with the supply chain and how to keep track of those. There is some improvement in capital investment. Often companies that are engaged with us and they have this type of data to support their product development see quicker time to market for their products. That also goes with regulatory compliance. And because of that quicker time to market, they see better capital asset utilization and less downtime. market growth, designing new products, products that are reacting to different market segments, and then also evaluating strategic direction to kind of, if their firm is looking or has chosen to take a new route towards green design or being more sustainable, it can give them a lot of insight into how best to take those strategic directions and boil those down to corporate action that their employees can actually implement. And so they do see a lot of value in participating in this project. So just as a summary, we really do see large potential for sustainability and quantitative assessment specifically of that sustainability to be an integral part of design, construction, operation of construction facilities, and all kinds of other business operations. But measuring that sustainability is essential to take advantage of opportunity. Getting the metrics right are critical to get better insight into firm and operations management. But there is really a potential to manage for sustainability, as we saw from the cost and from the impact and schedule variance control. You really can implement traditional management techniques to achieve quantitative sustainability improvements, and those are the lessons that we're embodying within the students that come out of here through this initiative, and it's the application of that 6-phase measurement framework. So when it's done right, quantitative sustainability assessment can be a really great tool in prioritizing initiatives and projects. Which part of the supply chain should I look at? Which activities generate the most impact? And if I was going to try to reduce impact quantitatively at the lowest possible cost, economically, where would I focus my effort? It helps to achieving real goals of sustainability. And it's not just meeting a label, but rather looking at a real emission that is the link between human activity and an ecosystem degradation. It also helps to align desires for profitability with desires for broader economic development, social equity, environmental protection, because we are doing this all in the context of managing for environmental impacts with at least marginal economic cost, so that there's ability to do cost-benefit analysis between the desire to achieve environmental and social goals while still making sure that economically we're not devastating anyone's profitability. We are always looking for new corporate partners, and we'll be soliciting those in August 2011. So if you're interested in participating in the class, please send me an email. I'd be happy to talk to anybody. I do have a bunch of acknowledgments. I have to thank my CE 226 students, all of my graduate students, National Science Foundation, and the partners that sponsored the projects that I talked about today. And so with that, I would be happy to answer any other questions in the last 10 or so minutes that we have. Are there any, Nicole?
I don't have any questions, and I do have a question, though, myself. I'm just curious, being in a student environment, what do you see as far as student interest in seeking sustainability-focused employment opportunities versus the demand or need from industry?
Right. So the students are incredibly interested in this, right? It used to be, especially being at Stanford, it used to be that I guess we'll say that the most kind of entrepreneurial and forward-thinking students would tend to go to electrical engineering, computer science. Being in Silicon Valley, that was always the case. Since this kind of sustainability movement has caught on, and we've really started to introduce it as something that you can manage for and design for and be a part of in the industry, the level of students has gone through the roof. The types of individuals we get that are interested in this are engaged and really want to make a big difference in the world. Now, as far as the connection between the need of industry and the interest of the students, what we always the first thing that we tell them is designing for sustainability is no different than designing for anything else. All we're doing is we're creating a metric, and then we're using conventional management techniques to achieve those metrics. And so therefore the base that you need in order to be able to do this kind of work is the same traditional management techniques, project management, project scheduling that you would do to do any project. The thing we layer on top of that is the sustainability measurement and metric portion. So therefore, when they're looking for positions, what they advertise, or the way we suggest that they market themselves, is not so much as some sustainability guru, but rather someone who understands project management and portfolio management and the ability to manage complex operations, but then also to do that in the context of sustainability, that they have all those basic tools to be able to run that. So if in fact the firm that they're working for wants to or has gone in that direction, they can apply those skill sets. But if the firm hasn't gone that way or is thinking about doing it in the future, they have a basic set of skill sets to provide to their employer at that time, and then be a big part of the sustainability movement if their firm decides to go that way in the future. Does that answer your question, Nicole?
Yes, it does. Thank you. And I have a few more that have come in the meantime. So what do you think of the emergence of the third pillar of sustainability, social assessment, in the set of life cycle thinking tools?
Right. So I guess we'll say that the social assessment part has always been kind of the neglected child of the assessment, and it's something that is an important part of this. The reason it's been so neglected is that the metrics that we have for it are pretty undefined and are tough to grasp in many cases. And of course, if you want to think that environmental impacts are value sensitive, social impacts are probably an order of magnitude more sensitive to value propositions. Where I think that's ultimately going to go is while most environmental impacts are not quantified in terms of dollars, I have a feeling that most of the social impacts at some point are going to be quantified in dollars or health impacts. And so I think that's ultimately where it's going to go. But I think it's a very good thing to see that third pillar receiving a lot more focus, because in the past it's been one that we haven't had a great grasp on, but we need to get a better handle around. Because as I had said at the start, those three sets of indicators are equally important, because all three of them are necessary for us to gauge the ability of our human systems and natural ecosystems to meet the needs of our population. And if we do that, not keeping into the context of meeting our basic human needs of equity and shelter and food and mobility, really we're not accomplishing what we need to. So I hope that answers the question, but it's kind of just my thoughts on where social impacts are going to go and why they're so important.
Thanks, Mike. Can you talk more about metrics? How are they tied into project goals and value propositions?
Sure. So in that case, I'll talk about the PPG example there. So one of their metrics by which they wanted to go to the DOTs, because especially in California, the state of California has signed on to the Kyoto Protocol, and of course AB 32 was a big deal here, the climate change initiative, and so therefore all of the California state departments were included as part of the California Climate Action Plan for reducing greenhouse gases and climate change gases. So when PPG was developing these new bridge decks, the value proposition for them was to go to Caltrans and say, look, we can bid on this project, or we can work with a contractor, bid on this project to do it at equal cost, but we'll also give you a hard and fast line for what the CO2 impact of this bridge deck is going to be, so that you can include it in your climate change plan budget for the Department of Transportation that they were allocated by the state. And this was actually a very desirable thing to Caltrans, because no one else had done this at that point. To say that, oh, in addition to an economic cost of building this bridge, we're also going to do this at a specific CO2 budget. And we're going to provide the tools for the construction management, not only to propose that, but much like we say we're going to build something for an X number of dollars, we're going to also say we're going to build it for this amount of CO2 and account for our CO2 over the course of construction to show you that we are meeting that goal. And that we are meeting our contract obligation in that case. And so in that case, it was used as a competitive bidding tool for a client that really valued that type of proposal. So and of course, depending on who the client is and what their priorities are, if you're looking at somebody like Steelcase building a factory or a facility for them, they have some very aggressive corporate goals for reducing footprints. And as a construction entity, going to them and saying, we will build you this facility for this amount of money and these specific impacts that we know that your company cares about, can be a very powerful bidding tool, especially if you can do that at equivalent cost, or at the very least be able to make cost-benefit comparisons to the client and saying, you know, we can meet these very aggressive goals if you're willing to pay this much, and if you're not, that's quite all right. We can still do the project and try to achieve the best numbers possible. So I hope that answers the question.
Yes. If it didn't, I would encourage that individual to contact you directly, as well as anyone else. Mike's information and contact information is up on the screen. And unfortunately, we've come to the conclusion of our hour, but I want to thank all of you for spending the past 60 minutes with us, and be reminded that a recording of both the audio and the PowerPoint will be made available on the FIATech website within the next few days at fiatech.org. And I just want to say thanks again, Mike, for sharing your work with us, and I hope you will all be able to join us next week when Dr. Mario Berger will be speaking to us about instrumenting civil infrastructure to increase its resilience, adaptiveness, and self-monitoring capabilities. So thanks again, and everyone enjoy your day.